Good day, everyone. My name is Maria Cristina C. Villaruel, and we will discuss about the chapter 3, which is about the symbolic logic. Introduction. Logic plays a very important role in mathematics. It is the foundation on which the discipline is built. Remember all the proofs you had to write to establish some theorems in algebra and geometry? You start with the given assumptions, use definitions, and perhaps some known results and argue logically to establish the conclusion. We consider mathematics as a language with its own symbols and grammar. These symbols may represent various mathematical objects like numbers, sets, or functions. The grammar will be the rules when combining these symbols. We apply logic to deduce properties of these subjects and rules based on some axioms. One cannot overemphasize the importance of logic in mathematics, but logic, or logical reasoning, is just as important in our everyday life. In this era of fake news, post-truths, false advertising, we must be able to discern what is true or false. We should be able to determine if a certain argument is valid or not. So here are the objectives. At the end of the lesson, you should be able to, first, identify the different statements. Second, classify statements as simple or compound statements. Third, write statements symbolically. Fourth, negate simple and compound statements. Fifth, use the truth table to determine the truth value of a statement. Sixth, determine whether an argument is valid or invalid using truth tables. And lastly, the seventh, identify logical patterns. Lesson 1. Logical statements and quantifiers. The great German philosopher, writer, and mathematician Gottfried Wilhelm von Leibniz, 1646 to 1716, was among the first to realize the need to formalize logical argument forms. It was his dream to create a universal formal language of signs that would translate all philosophical arguments to symbols and variables, or the symbolic logic, in place of natural language, such as English, in order to remove vagueness. A statement or a proposition is a declarative sentence that can be objectively determined to be true or false, but not both. Consider this example. As you can see, the sentence says, radioactive ants can make you a superhero. Buroy Loganay Festival is the festival in Symbolic Antique. 13 plus 12 is equals to 25 are considered to be statements because it can be determined as true or false but not both. Radioactive ants can make you a superhero. It is false. Buroy Loganay Festival is the festival in Symbolic Antique. It is true. And lastly, 13 plus 12 is equals to 25, which is true. The second one is, the sentence says, make me a pot. What makes a better student? And the expression, wow, are considered to be not statements because it cannot be determined as true or false. Make me a pot, command sentence, or cannot be determined as true or false. What makes a better student is a question or interrogative sentence and cannot be determined as true or false. The expression wow is an exclamatory sentence, cannot be determined as true or false as well. Another examples are example recognizing statements. Decide which of the following are statements and which are not by writing the word yes before the number if it is a statement and no if it is not a statement. Letter A, bamboo is the strongest tree. Letter B, do you believe that bamboo can be considered as a grass? Letter C, hey, that's awesome. Letter D, 28 divided by 7 plus 6 minus 2 is equals to the square root of 49. Letter E, this house is made up of bamboos. And letter F, for me, seeing you happy makes me inspired. So here are the solutions. For letter A, the statement, bamboo is the strongest tree. So yes, it is a statement. And because it can be judged as true or false in an objective manner. For the letter B, do you believe that bamboo can be considered as a grass? It is a no, because it is not a statement and because it is a question. And for letter C, hey, that's awesome. So, also no, because it is not a statement and because it is an exclamation. So, for the letter D, 28 divided by 7 plus 6 minus 2 is equals to the square root of 49. Yes, it is a statement and it can be judged as true or false in an objective manner. For letter E, this house is made up of bamboos. Also yes, because it is a statement and it can be judged as true or false in an objective manner. For the letter F, for me, seeing you happy makes me inspired. It is a no, because it is not a statement and it gives only an opinion. So, here are the simple statements and compound statements. A simple statement contains only one idea. Here are the examples. Your uniform is red. This university is surrounded by beautiful trees. Muscovado sugar is very nutritious. A compound statement is formed by joining two or more simple statements with a connective. Here are the examples. April studied for 5 hours and she got the highest score. So, the connective that we use for this sentence is and. Second one is Mary will run in a mini triathlon or she will play in the campus tournament. For this one, we use the connective or. For the last, if you are vaccinated with anti-COVID vaccine, then you are 80% safe from the infection of virus. For this sentence, we use the connective if and then. Example, classifying statements as simple or compound. Classify each statement as simple or compound. Letter A, our school mascot is an ant. Letter B, if you register to Wi-Fi service, then you will get 3 days of free access. Letter C, tomorrow is the last day of registration for online classes. And letter D, this time of pandemic, I will stay at home or go for a vacation. So here are the solution. For letter A, our school mascot is an ant. There are no connectives involved, so this is a simple statement. Letter B, if you register for Wi-Fi service, then you will get 3 days of free access. This if-then statement is compound because they are connectives. Letter C, tomorrow is the last day of registration for online classes. Simply, this is a simple statement. And letter D, in this time of pandemic, I will stay at home or go for a vacation. For this, ultimately, this statement could be restated as I will stay at home or I will go for a vacation, which makes it a compound statement because there is a connective which is the or.
So let's go to quantified statements. When we say quantified statements, it involves terms such as all, each, every, no, none, some, there exists, and at least one. The first 5, all, each, every, no, and none, are called universal quantifiers because they either include or exclude every element of the universal set. The last 3, some, there exists, and at least one, are called existential quantifiers because they claim the existence of something but do not include the entire universal set. So as we can see, all, each, every, no, none are the terms that use in universal quantifiers, and some, there exist, and at least one in existential qualifiers. Here are examples of quantified statements. Every student in the university are required to make their LMS account. No student should be left behind. Some people who are skilled in bamboo furniture making are also skilled in pottery making. There is at least one professor in this school who is not fully vaccinated. The terms that we use are every, no, some, and at least one are the terms examples of quantified statements. Now let's go to negation of statement. The negation of a statement is a corresponding statement with the opposite truth value. The typical way to negate a simple statement is by adding the word not. If the statement already includes the word not, then remove it to form negation. Here are examples of negation. Pacquiao will win on his fight. So the negation of this statement is Pacquiao will not win on his fight. I uploaded my work today. The negation is I did not upload my work today. My phone cannot access the internet. My phone can access the internet. 6 plus 7 is not equal to 13. 6 plus 7 is equal to 13. Let's go to the negations of quantified statements. We can summarize the negation of quantified statements as follows. All do or every. The negate of this is some do not. Some do, all do not, or none do. Some do not, or all do, or every. None do. The negate of this is some do. All are, or some are not. And some are, none are, or all are not. This diagram should help you remember the negations for quantified statements. The statements diagonally opposite each other are negations. All are, or some are not, and some are, or none are, or all are not. In example 3.3, the writing negations of quantified statements. Write the negations of each of the following quantified statements. So the quantified statements, number 1 is every student in the university are required to make their LMS account. Therefore, the negation of quantified statements are some students in the university are not required to make their LMS account. Some people are skilled in bamboo for furniture making. The negation is no people are skilled in bamboo furniture making. There is at least one professor in this school who is not fully vaccinated. The negation of the quantified statements is all professors in this school are fully vaccinated. No student should be left behind. And the negation of these quantified statements is at least one student should left behind. So let's go now in symbolic notation. Symbolic logic uses letters to represent statements and special symbols to present words like and, or, and not. Use of this symbolic notation in place of the statements themselves allows us to analytically evaluate the validity of the logical behind an argument without letting bias and emotion cloud our judgment. We often use parentheses in logical statements when more than one connective is involved in order to specify an order. Simple statements in logic are usually denoted with lowercase letters like P, Q, and R. So examples. Write it in conjunction, disjunction, conditional, and biconditional, and translate to symbol the two statements below. We could use P to represent the statement I am vaccinated and Q to represent the statement I will be safe from the spread of COVID-19. So in letter A, conjunction, P is I am vaccinated and Q is I will be safe from the spread of COVID-19. To make the statement conjunction, we use the connectives and. Therefore, the statement would be I am vaccinated and I will be safe from the spread of COVID-19. So in symbol, P and Q. In letter B, disjunction, the P is I am vaccinated and the Q is I will be safe from the spread of COVID-19. To make the statement disjunction, we use the connective or. Therefore, the statement would be I am vaccinated or I will be safe from the spread of COVID-19 in symbol P or Q. In conditional, the P is I am vaccinated and the Q is I will be safe from the spread of COVID-19. To make the statement conditional, we use the connectives if and then. Therefore, the statement would be if I am vaccinated, then I will be safe from the spread of COVID-19. In symbol P, then Q. And last, in biconditional, the P is I am vaccinated and the Q is I will be safe from the spread of COVID-19. To make the statement biconditional, we use the connectives if and only if. Therefore, the statement would be I am vaccinated if and only if I will be safe from the spread of COVID-19. So in symbol, P, if and only if, Q.
Symbol for a negation. Earlier, we discussed about the negation of a simple statement. Here, we introduce the symbol tide or curl to represent a negation. For example, P represents the statement I am vaccinated. P is equal to I am vaccinated. Its negation is I am not vaccinated. Example 3.4. Writing statement symbolically. Let P represent the statement it is cloudy and Q represent the statement I will go to the beach. Write each statement in symbols. P represent it is cloudy and Q represent I will go to the beach. A. I will not go to the beach. Solution. First, identify the connector and or if, then if and only if keyword in each statement and rewrite using the appropriate symbol. I will not go to the beach. This is the negation of statement Q in symbol negation Q. It is cloudy and I will go to the beach. It is cloudy and I will go to the beach. This is the conjunction of P and Q in symbol P and Q. C. If it is cloudy, then I will not go to the beach. Solution. If it is cloudy, then I will not go to the beach. This is the conditional of a P and the negation of Q in symbol P, then negation Q. I will go to the beach if and only if it is not cloudy. Solution. I will go to the beach if and only if it is not cloudy. This is the conditional of Q and not P in symbol Q, if and only if, negation P. Example 3.5. Translating statements from symbols to words. Write each statement in words. Let P represents my performance in Jack 4 is excellent and Q represents my performance in art class is poor. P represents my performance in Jack 4 is excellent and Q represents my performance in G1 is poor. Negation P. Solution. My performance in Jack 4 is not excellent. P or Q. My performance in Jack 4 is excellent or my performance in G1 is poor. Negation P, then Q. If my performance in Jack 4 is not excellent, then my performance in G1 is poor. Q if and only if P. My performance in G1 is poor if and only if my performance in Jack 4. Q if and only if is excellent. Q and P. My performance in G1 is poor and my performance in Jack4 is excellent. Now, let's move on to Lesson 2, Truth Tables, Tautology, Contradiction, and Contingency. Truth values for a negation. The truth table for the negation of P looks like this. There are two possible conditions for the statement P, true or false, and the table tells us that in each case, the negation P has the opposite truth value. If the statement P is true, its negation is fake. And if statement P is false, then its negation is true. Truth values with two simple statements. If we have a compound statement with two component statements P and Q, there are four possible combinations of truth values for these two statements. Number 1, P and Q are both true. Number 2, P is true and Q is false. Number 3, P is false and Q is true. And number 4, P and Q are both false. Conjunction and. The conjunction P and Q is true only when both P and Q are true. The truth table below summarizes the possibilities for the conjunction I bought a new computer and a new iPad. P represents I bought a new computer and Q represents I bought a new iPad. Both computer and iPad, P is true and Q is true, that's why P and Q is true. Both computer, not iPad, P is true and Q is false, that's why P and Q is false. Both iPad, not computer, P is false and Q is true, that's why P and Q is false. Both neither, P is false, Q is false, and P and Q is false.
I'm Kenny Aguilian and I will discuss you about disjunction or OR. The disjunction P or Q is true when either P or Q are both are true. It is false only when both P and Q are false. And the truth table below summarizes the possibilities for the disjunction. And this is the example. I bought a new computer or a new iPad. And as you can see in the table, they have a P as a hypothesis and Q as a conclusion. Therefore, if hypothesis P is true and the conclusion is true, and the answer is true. But if the hypothesis is false and the conclusion is false, the answer is false. Next is letter C, that conditional or if-then. A conditional statement, which is sometimes called an implication, consists of two simple statements using the connective if-then. The first component is called the hypothesis or antecedent. The second component is called the conclusion or consequent. The conditional statement P implies Q or if-then is false only when the hypothesis antecedent P is true and the conclusion or consequence Q is false. And the truth table below summarizes the possibilities for the conditional. That example is, if the Lakers will win tomorrow, then they make the playoffs. So as you can see in the table, they have a P or a hypothesis and a Q or a conclusion or consequence. That if the hypothesis P is true and the conclusion Q is true, therefore the answer is true. But if the hypothesis P is true and the conclusion Q is false, the answer is false. Next is letter D, the biconditional or if and only if. A biconditional statement is really two statements. It's the conjunction of two conditional statements. In symbols, we can write either P, if and only if, or open parenthesis P, if, and Q and close parenthesis, and open parenthesis Q, implies P or if and close parentheses. And the biconditional statement P if and only if is true when P and Q have the same truth value, and it's false when they have opposite truth value. And as you can see in the example or a table, they have a P that have a hypothesis and Q as a conclusion. So as you can see, they have, if hypothesis true and conclusion is true, the answer is true. But if the hypothesis P is false and the conclusion Q is false, and the answer is true. So this is not the difference of biconditional in the conditional. So this is the complete list of truth values for conjunction, disjunction, conditional, and biconditional. Example, constructing a truth table. Construct a truth table for the statement negate P or Q. Solution, step 1. Set up a table as shown. The table order in which you list the TS and FS doesn't matter as long as you cover the all possible combination. For consistency, we'll always use the order or TTF for P and TFTF for Q when these are the only two letters in the logical statement. And here is the table below. Step 2. Find the truth values for negate P by negating the values for P and put them into a new column or column 3 marked negate P. Truth values for negate P are opposite those for P. Step 3. Find the truth values for the disjunction, negation of P or Q. Use the T and F values for negation of P and Q in column 3 and 2 respectively. Remembering that a disjunction is false only when both components are false. The truth values for the statement negation of P or Q are found in the column 4. And remember the definition. The disjunction is false only when both components are false. Example, constructing a truth table. Construct a truth table for the statement negation of open parenthesis P if negation of Q close parenthesis. Solution, step 1. Set up a table as in example number 1. And as you can see in the table, they have P as a hypothesis and Q as a conclusion. Step 2. Find the truth values for negation of Q by negating the values for Q and put them into a new column 3 marked negate of or negation of Q. Truth values for a negation of Q are opposite those for Q. And as you can see, they have a column 3, and in the left side, this is a statement. Step 3. Find the truth values for the implication P if negations of Q using the values in column 1 and 3 respectively. Remember that an implication is false only when the antecedent is true and the consequent is false. Open parenthesis, in our example, antecedent P, consequent if negation of P or negate P. And as you can see in the table, they have a column 1 as hypothesis and the column 3 is conclusion. And remember the definition that the conditional is false only when the antecedent is true and the consequent is false. Step 4. Find the truth values for the negation or negation of open parenthesis P if negation of Q close parenthesis by negating the values for P if negation of Q in column 4. The truth values for negation of open parenthesis P if negation of Q are in column 5. Notice that the statement is true only when P and Q are both true. And as you can see, they have a column 4 and a column 5. Example, constructing a truth table. Construct a truth table for the statement P or open parenthesis Q if R close parenthesis. Here's the solution. Step 1. Set up a table as shown. The order in which you list the TS and FS doesn't matter as long as you can cover all the possible combination. For consistency, we'll always use the pattern shown for three letters. The three letters are P, Q, R.
Step 2 of constructing the truth values is to find the truth value for the statement in parentheses Q implies R. Let's remember the definition of conditional. The conditional is false only when the antecedent is true and the consequent is false, and the rest is true. Let's look at the column of Q and R. Q as the antecedent and R as a consequent. See that the rule of conditional implies at the second and sixth rows of column Q and R, and the rest is all true. Step 3. Find the truth values for the disjunction P or Q implies R, using the values for P from column 1 and those for Q implies R from column 4. Let's always remember that the disjunction is false only when both components are false. The truth values for the statement P or Q implies R are found in column 5. Notice in column 5 that the statement is true unless P and R are false, while Q is true. There are three compound propositions: the tautology, contradiction, and contingency. A tautology is a compound proposition that is always true, regardless of the truth values of the propositions that occur in it. A contradiction is a compound proposition that is always false, while a contingency is neither a tautology nor a contradiction. Let's determine if the given proposition is a tautology, contradiction, or contingency, using the truth table of the example number 1. P or Q and not P if and only if P or Q. Since the result in the final column of the truth table showed to be true, then the proposition is said to be a tautology. Example number 2. P implies Q if and only if negating the not Q implies not P. As you can see in the last column of the truth table, it appeared that all the values are false. Therefore, the proposition in this problem is in contradiction. In example number 3, P and not Q implies not P or Q shows that the proposition is contingency because the result of truth table showed a combination of true and false. It is neither a tautology nor a contradiction. Conditional and related statements. Equivalent forms of the conditional. Every conditional statement can be stated in many equivalent forms. It is not necessary to state the hypothesis or antecedent before the conclusion or consequent. For instance, the conditional, if I live in Sibalom, then I must be an Antiqueño, can also be stated as, I must be an Antiqueño if I live in Sibalom. Here are some of the various forms that may be used to write a conditional statement. According to Hoffman et al. 2014, every conditional statement P implies Q can be written in the following equivalent forms. If P then Q, the equivalent is every P is a Q. If P Q, the equivalent is Q if P. P only if Q, the equivalent is Q provided that P. P implies Q, the equivalent is Q is a necessary condition for P, while Q whenever P, the equivalent is P is a sufficient condition for Q. Let's try this example. The number is an even number provided that it is divisible by 2. Let's write the equivalent form of this statement. The statement, the number is an even number provided that it is divisible by 2, is in Q provided that P form. The hypothesis or antecedent is it is divisible by 2, and the conclusion or consequent is the number is an even number. Thus, it's if P, then Q form is, if it is divisible by 2, then the number is an even number. Another example. Today is Friday, only if yesterday was Thursday. The statement, today is Friday, only if yesterday was Thursday, is in P only if Q form. The hypothesis or antecedent is today is Friday. The conclusion or consequent is yesterday was Thursday. Its if P then Q form is, if today is Friday, then yesterday was Thursday. Last example. Every square is a rectangle. The statement, every square is a rectangle, is in every P is a Q form. The hypothesis or antecedent can be stated as, a geometric figure is a square. The conclusion or consequent can be stated as, it is a rectangle. Its if P then Q form is, if a geometric figure is a square, then it is a rectangle. Let's go to the three related statements of conditional statement: the converse, inverse, and contrapositive. The converse of P implies Q is Q implies P. The inverse of P implies Q is not P implies not Q. Then the contrapositive of P implies Q is not Q implies not P.
This is the definition about the statement related to the conditional statement. The converse of P implies to Q is formed by interchanging the hypothesis and antecedent P with the conclusion and consequent Q. The inverse of P implies to Q is formed by negating the hypothesis and antecedent P and negating the conclusion and consequent Q. The contrapositive of P implies to Q is it is formed by negating both the hypothesis and antecedent P and the conclusion and the consequent Q and the interchanging these negated statements. Sample number 3. Write the converse, inverse, and the contrapositive of the statement, if you stayed at home, then you are safe. In this statement, if you stayed at home as our hypothesis, and then you are safe as our conclusion. The solution is converse. If you are safe, then you stayed at home. In this statement, we implies the hypothesis and the conclusion. The inverse statement, in inverse statement, if you didn't stay at home, then you aren't safe. In this statement, we negate both hypothesis and conclusion. Contrapositive, if you aren't safe, then you didn't stay at home. In this statement, we implies and negate both the hypothesis and conclusion. In this table, this shows the truth tables for conditional and related statement. Conditional statement. P implies to Q, and the converse is Q implies to P. And in the inverse, the negation of P implies to negation of Q. And to the contrapositive, the negation of Q, it implies to negation of P. For example, all even numbers are divisible by 2. Formulate a statement as a conditional and give its converse, inverse, and contrapositive. The conditional statement form of the statement is, if it is an even number, then it is visible by 2. And in converse statement, if if a number is visible by 2, then it is an even number. In in the inverse statement, if it is not an even number, then it is not divisible by 2. And in contrapositive statement, if it is not visible by 2, then it is not an even number. And now we are going to lesson 3, which is valid arguments. An argument is consists of a set of statements called premises and another statement called the conclusion. An argument is valid if the conclusion is true whenever all the premises are assumed to be true. An argument is invalid if it is not a valid argument. Let us look at the valid arguments given below. Number 1. All dogs are hairy. Cotton is a dog, therefore cotton is hairy. Number 2. All dogs are hairy. My pet Donut is not hairy, therefore Donut is not a dog. Number 3. All cats are mammals. All mammals are animals, therefore all cats are animals. Arguments of the above form are always valid and satisfy valid arguments form called modus ponens, modus tollens, and syllogism respectively. To define the form of these arguments, recall the conditional P implies to Q is equivalent to the universal statement all P are Q. So we can have restate the statement the statement above as all P are Q and P implies to Q. We have the following general forms. The modus ponens or law of detachment. If it is a dog, then it is hairy. P implies to Q. Cotton is a dog, and the underlying phrase is P. Therefore, cotton is hairy, therefore Q. Modus tollens, law of contraposition. If it is a dog, then it is hairy, which is P implies to Q. My pet Donut is not hairy, which is negation Q. Therefore, cotton is a dog. Therefore, negation P. Syllogism. If it is a cat, then it is a mammal. If it is a mammal, then it is an animal. Therefore, if it is a cat, then it is an animal. We can use truth tables to show the validity of these arguments. In particular, we find the truth values of the conditional whose premises is the conjunction of the premises and the conclusion is the given conclusion in the argument, that is, number 1, modus ponens, open parenthesis P implies to Q, close parenthesis, and P implies to Q. Number 2, modus tollens, open parenthesis P implies to Q, close parenthesis, and Q negate Q implies to P. Number 3, syllogism, open parenthesis P implies to Q, close parenthesis, and open parenthesis Q implies to R. If the statement is true for each of the 4 cases in the truth table, then the argument is valid. In this case, we call the statement a tautology, and the conditionals given are in facts and implication. We have the following truth tables. Number 1 is modus ponens, and number 2 is modus tollens. And number 3 is syllogism. Note in this syllogism table, we have the 3 statements, the P, Q, and R. Example, deciding if an argument is valid, determine if the following argument is valid or invalid. If the ad campaign is success, the marketing management won't lose her job. The marketing manager lose her job. Therefore, the ad campaign wasn't a successful.
Hi everyone, I am Angeline Malones and I'm going to discuss the example of syllogism, which is if the ad campaign is a success, the marketing manager won't lose her job. So solution, step 1, write the argument in symbols. Let P equals the ad campaign is a success and let Q, the marketing manager, loses her job. Translated into symbol, P implies the negation of Q premise, then Q premise, and the conclusion is the negation of P. A line is used to separate the premises from the conclusion, and the three triangular dots mean therefore. Step 2. Write the argument as an implication by connecting the premises with a conjunction and implying the conclusion. Premise 1 and premise 2, therefore a conclusion. P implies the negation Q and Q, therefore the conclusion is the negation of P. Step 3. Construct a truth table for P implies the negation Q and Q, therefore the negation of P. Step 4. Determine the validity of the argument. Since all of the values under the conclusion are true, the argument is valid. Example, deciding if an argument is valid, so decide if the argument is valid. P implies R, Q, and R, P. Therefore, the negation of Q implies P. Solution, step 1, write the argument in symbols, so it is already done. Then step 2, write the argument as an implication by connecting the premises with a conjunction and implying the conclusion. Premise 1 and premise 2 and premise 3, then conclusion. So P implies R and Q implies Q and R and P. Therefore, the conclusion is the negation Q implies P. Step 3. Construct a truth table. When there are 3 premises, we will begin by finding the truth values for each premise and then we'll work the conjunction from left to right. So P implies R and Q and R and P. Therefore, the negation Q implies P. Then step 4, determine the validity of the argument. It is a tautology, so it is valid. Then let's go to the fallacies. So consider the 2 invalid arguments. Number 1, all dogs are hairy, my pet Cotton is hairy, therefore Cotton is a dog. The number 2, all cats are mammals, my pet Donut is not a cat, therefore Donut is not a mammal. So these are example of 2 invalid argument forms, the fallacy of the converse and the fallacy of the inverse respective. In symbols, these are the form. So fallacy of the converse, P implies Q, Q, therefore P. Fallacy of the inverse, P implies Q, then the negation of P, therefore the negation of Q. Let us look at the truth tables for these 2 arguments. We consider the 2 conditionals. P implies Q and Q implies P and P implies Q, and negation of P implies the negation of Q. So number 1, it is the fallacy of the converse. P implies Q and Q implies P. Then number 2, fallacy of the inverse. P implies Q and negation of P implies the negation of Q. Observe that unlike the valid arguments forms, the arguments given above are not tautologies since they are not true for each of the 4 cases. They are called fallacies. The arguments P implies Q and Q implies P is false when P is true and Q is false. And P implies Q and the negation of P implies the negation of Q is false when P is false and Q is true. So the other fallacies. We also have fallacies other than the forms given above. In fact, we probably encounter these fallacies more frequently. So number 1, ad hominem. The argument is based on the character of the opponent instead of the argument itself. This may also involve insulting the opponent to make opponent's arguments seem false. So example, Maria wears leather shoes, so she cannot be a vegetarian. So number 2, ad populium. This fallacy occurs when an argument is assumed to be valid since many people believe in it. Example, surveys indicate that 55% of the population believe that the use of contraceptives is dangerous. Therefore, contraceptives should be banned. Number 3. Appeal to authority. The argument is claimed to be valid because a famous or famous person who is not expert in pertinent field supports it. Example, brand X is the best toothpaste since our president uses it. Number 4. False cause. This fallacious argument correlates to events even if unrelated. Example, every time I go to sleep, the sun goes down. Therefore, my going to sleep causes the sun to set. Number 5. Hasty generalization. In this fallacy, a generalization is made based on a few examples supporting the claim. Example, I don't excel in tennis. I also don't excel in volleyball. Therefore, I don't excel in sports. There are two big lessons to be learned in this section. First, the validity of an argument is not about whether the conclusion is true or false. It's about whether the conclusion follows logically from the premises. Second, sometimes an argument can appear to be legitimate superficially, but if you study it carefully, you may find out that it's not. Example, determine whether the following arguments are valid using the given forms of valid arguments and fallacies. So letter A, P implies Q, then Q, therefore it is Q. Letter B, the negation P implies Q, then the negation Q, therefore it's P. Letter C, the negation P implies the negation Q, then the negation Q, therefore it's negation P. Letter D, the negation R implies S implies T, therefore it's the negation R implies T. Then, let's go to the solution. Letter A, this is the modus ponens or the law of detachment, therefore a valid argument. So P implies Q, then Q, therefore it is Q. Letter B, this fits the modus tollens or the law of contraposition with the statement the negation P substituted in place of P, so it is valid. The negation P implies Q, then the negation Q, therefore it is P. Letter C, this fits the fallacy of the converse using statement the negation P in the negation Q rather than P and Q, so it is an invalid argument. So the negation P implies the negation Q, then the negation Q, therefore it is the negation P. Last, the letter D, this is the law of syllogism with statements the negation R, S, and T, so the argument is valid. So the negation R implies S implies T, therefore the negation R implies T.